All right, so we have a few lessons left in the AB calculus. We've done a lot of integration and finding area, bounded by a curve and the x-axis. Today's lesson opens that up a little bit in terms of integration. For today's lesson, we're not just going to be bounded by the x-axis, but what we're going to be trying to do is find the area between two curves. So if you look at right here, this first region, I'm going to be trying to find the area between this top function and this bottom function. There's a formula that goes along with it, but I have this book open here just to show you a little bit about the why and kind of where the formula comes from. The formula is pretty easy. As you start doing some problems, there's always some questions that arise from students, but we'll take care of that, when the time comes. But basically, if I want to find the area between these two curves, well, think about what we're doing. We're finding the area under that top curve bounded by the x-axis, so this big pink region. So this is just us integrating f, that top function, from a to b. We're finding all this area. And then we want to get rid of this bottom area. Well, that's just the integral of g from a to b. That's what we've been doing this whole time. So that leads us to the formula. If we want to find the area between two curves, we just integrate and we take the top function minus the bottom function from a to b. And like I said, that's basically our formula. I think when you guys do the homework and we go into, some of the in-depth stuff next class, some questions will come up with negatives and things like that. But bottom line, when I talked about a while back, the difference between calculating a definite integral and finding area, a definite integral can be negative, but what we're doing in this section is we're finding the area of a region between two curves. Basically, your answer is always going to be positive, no matter if that region is above the x-axis, whether it's, here's an example here, whether that region is below the x-axis, here's the x-axis, or whether that region gets cut by the x-axis. We're always going to be doing the top function minus the bottom function, and when we do that, our area is always going to end up being positive throughout our work. So that's not really something we need to keep in mind. When you do the top function minus the bottom function, the answer turns out to be negative. And like I said, we've basically been doing this every single time anyway. When we integrate, think about what we're doing. If I have some function and I'm trying to find the area under that curve, well, we're just integrating this function from a to b. What we're actually doing is subtracting two functions. It just so happens our bottom function is the x-axis, which is 0. So every single time we've been integrating, technically we've been integrating the function minus 0. We just never put the minus 0, but that's what it's been doing. That's why integration is bounded by the x-axis in general, is because the bottom function most times is 0. Or if it's below the x-axis, so if I say want to find this area, well, what we've been doing is we've been integrating the function. Well, if you think about it, the reason this turns out to be positive is because when we just integrate the function right here, this integral is negative, but what we're going to be doing is if we wanted this area to be positive, if I wanted to find the area below the x-axis, I could take 0 minus the function if I really wanted to. This would calculate the actual area, not necessarily the definite integral. There's a difference between calculating a definite integral, because most often that's finding the change in the original function, versus calculating the area of a region. We're doing something different now. We're just calculating the area of a certain region, not necessarily getting into how much the original function is changing. Okay? So again, we're just going to take the top function minus the bottom function and integrate from one x value to the other x value. And that's basically the lesson. There's not a lot other than that behind it. So I have some examples. I might just put up the key for some of these for you to jot down once we get into past the concept stuff, but let's just dive in. So if I want to find the area of a region between two curves, well, if our functions are continuous and one function's always below the other function, then the area of the region bounded by the graphs and the vertical lines a and b is going to be the area equals the integral from a to b of the top function minus the bottom function. which is all that stuff I was just talking about in the book. Notice the top function is the one that is all those y values are greater than or equal to the other function. So that's how we know what the top function is. Well, let's apply. So find the area of the region bounded by the graphs of y equals 2 minus x squared and y equals x. So the first thing I want to do is sketch this region. Let's see what that is.
Attention staff and students that are remaining in the building. If Mr. Sheely could please call 12100. Mr. Sheely, call 12100. Thank you.
Oh, Mr. Sheely. Okay. So I'm going to sketch. Well, I know that g of x equals x. That's just the line y equals x. So that's your line right here. And it's not going to be a perfect sketch. I'm really just trying to see which function's on top, to be quite honest, which one's on bottom. Y equals 2 minus x squared. Well, think about what that does in transformations. That takes our parabola, shifts it up 2 units, and then reflects it over the x-axis. So that's going to put your vertex here. We technically could calculate the x-intercepts, but we know the parabola is going to look like this. Like I said, all we truly care about is which graph's on top and which one's on bottom. So we're going to be finding this region right here. Okay, so if I want to find that area, again, it doesn't matter if some of your area is above the x-axis, below the x-axis. This is really different than doing definite integrals. We are just finding the area between two curves. We take the top function minus the bottom function, and we integrate. Well, what's going to happen now is we're going to have to find intersection points. And I mentioned that there are, those four free functions you get to use your calculator on the AP test. You get to solve any equation by setting it equal to 0 and finding x-intercepts. You get to do math 8, so find derivatives. You get to do math 9, which is definite integrals. And the other one you could do without showing any work is finding intersections of functions. Well, this has no calculator. So we got to find those intersections by basically doing a system. Just set our two equations equal to each other. So this is going to find those x values where they cross. So let's see, x squared, if I add x squared, subtract 2, plus x minus 2, factor. So x equals negative 2 and 1. Those are going to be what we integrate to and from. So we're going to integrate from negative 2 to positive 1. Oh, that's pretty close in my estimations here, a little off. So our area, we're going to integrate from negative 2 to positive 1 of the top function, 2 minus x squared, minus the bottom function, which is x, dx. And then we are just going to go ahead and integrate this. We're going to do our fundamental theorem of calculus. So 2x minus 1/3 x cubed minus 1/2 x squared from negative 2 to 1. We're going to plug in that top value. So 2 minus 1/3 minus 1/2 minus parentheses. And then plug in negative 2. So negative 4. Okay, negative 8 times negative 1/3 is positive 8/3. And then 4 times negative 1/2 is negative 2. FRQ, we can leave this answer. I'm just going to go ahead and give you the answer because I know you guys can work with fractions. The answer is 9/2. So that is the area from negative 2 to 1 bounded by those two functions. Top function minus bottom function. All right. Next one, very similar. Find the area of the region bounded by y equals cosine of x and y equals x squared. So we're going to start off similar. We're going to go ahead and sketch that region. And again, mainly we're trying to see which function's on top, which one's on bottom. On the AP test, they do a really good job of showing you the graphs. I actually probably need to redo these and just give the graphs to begin with, to be quite honest. They usually do. So y equals x squared is your parabola. Right there. And then cosine of x starts here and looks something like this. Something like that. So what we care about is this region right here. I want to find the area of that region. So we're going to do the top function minus the bottom function. The top function is cosine. Bottom function is x squared. But again, we have to find these limits of integration. It's calculator. So little tip of what happens on the AP test. A lot of times on a calculator active question like this, you'll find these limits. I would set, so I know you get to do this for free on the test, but I would at least show the equation that you're solving right here before you just write, two random answers. So x is going to equal, well, our a value, I guess I should say, is negative 0.8241323. Just graph both and calculate the intersection. Our right limit of integration is 0.8241323. So here's a little tip on the AP. A lot of times your limits of integration are going to be some gross numbers like this. They encourage you guys to list, a equals blank, b equals blank, because then as you set up your integrals as you go through the problems, because remember, you might have to use these limits, through 4 different parts of a free response question. And now you can just write a and b, you've defined those values. So when we set up our integral, now we just say from a to b of cosine of x minus x squared. Like this is fully allowed right here after you define these. If there's a part B to this question, they'll still use your values that you stated in part A. That's allowed. And then you just pull out math 9, you enter this integral, and you get 1.095. All right. A few left. So there are some little things that can happen. If you look at example 3 here, so I gave the graphs. I got smart and gave the graphs here. If you notice what happens on this one is the top and bottom functions switch places. They switch roles. So if you look from, they actually give you the limits too. If you look from -2 to 0, well, f of x is above g of x. And then from 0 to 2, g of x is now above f of x. So what that means is we have to set up 2 different definite integrals and add them together. So we can't just state g of x minus f of x because they switch at some point in the interval. So we have to set up both. So I'm going to go ahead and just, I don't know why I listed out all of it on my key. So instead, I'm not going to. So my area is going to equal. If I want to find the area of the left part, it's from -2 to 0. And our f function is above the g function. So I'll say f of x minus g of x. Remember, when functions are named, you can just use them. Plus, so this is a case where when they're grading, if you don't put the dx, you're probably not going to get full credit because you have a definite integral and then you're doing more. In general, if you're just setting up one integral and you forget the dx, usually you'll be okay. I would try to remember to put it every single time, especially for these cases. And then we're going to integrate from 0 to 2, but now our g function is above the f function. So 0 to 2 of g of x minus f of x. And then we would just go through the integration. Again, I'm not as concerned about that process because we've done so much of that. So I'm just going to give you the answer here. I mainly wanted to talk about when the 2 functions switch within an interval. So that equals 24. Isn't that crazy? You have those 2 curves, looking all weird, and it just turns out to be 24. Interesting. All right. The next one, so now we have 3 functions. Find the area bounded by f, g, and h. Well, let's see what in the world is going on here. So let's sketch this, and let's find out. So it doesn't matter what order you do it. So y equals x cubed is that one. So that's f of x. Y equals x plus 6. So now that's our line that y-intercept of 6, slope of 1. This is going to look pretty booty, by the way, but so let's just say that's 6. And slope of 1. Basically that line looks like this. And the last one is negative 1/2 x. So now that has a y-intercept of 0, slope of negative 1/2. So it's going to look something like this. Again, there's no, I don't have increments or anything. But here's our region, right here. And if this is in class, a lot of times I have students try this one on their own, and this causes a lot of confusion for some students. They'll try to subtract all three functions. They'll do like f minus g minus h, stuff like that. When you guys are finding area, you're only ever going to subtract two functions. The difference on this one, it's actually really similar to the previous problem, how at some point the top and bottom functions switch. That's what happens here. If you look at this left, basically left of the y-axis right here, we have our f function. No, I lied. I labeled these very poorly. I apologize. That's f, is the x cubed. This one's g. And then this one is h. So if you look left of the y-axis, our g function is above the h function. So we're going to integrate from wherever these cross here to 0 of g over h. And then after, on the right side of the y-axis, now we have the g function on top of the f function. So again, we just set up two different integrals and we add them together. But we do need to figure out where these things cross. We got to find these intersection points. So first, let's figure out where g and h intersect. So you can either set these two things equal to each other or use your calculator. But the intersection points of all of these are negative 4, 0, and 2. So g and h intersect at negative 4. H and f intersect at 0. And then g and f intersect over here at 2, if you solve those systems. Now I'm just going to put the key up for this one. Here it is. So on that left one, I'm doing g minus h from negative 4 to 0. And then I'm doing g minus f from 0 to 2. Make sure you put dx behind both of them. And that turns out to be 22. The last one. So in regular AB Calc, we spend a day on these types, and then we spend a day on sideways. So what happens if our two functions, well, let me show what I mean here. So on the last one, it says find the area x equals 2 minus y squared and x equals y. So sometimes we are going to have everything be in terms of y. Our limits of integration, our y limits of integration. We're going to be looking at the right function minus the left function. And I want to show you how you know or when you know that's going to be the case. So the first thing I want to do is graph these. This is our last one. Well, x equals y is just y equals x. So that's our normal line going through the origin. X equals 2 minus y squared. Well, if you think back to Algebra 2 and probably pre-cal, that x equals y squared graphs are sideways parabolas. And when it's negative y squared, it opens to the left right here. And the 2 means instead of shifting up 2, it shifts right 2. Basically, the graph looks something like this. Now we can do what we did on the previous problems, but if you look, there's an issue. You know, if we do top minus bottom, look what's happening. Okay, well here we have the line on top of the curve, so that's not an issue. But then if you look right here, as you go past where those graphs intersect, now we have a graph on top of itself. So we have to find that area. Now you have some options. You could solve this thing for y, and then you get plus or minus. And so the plus would be the top part of that curve, and the minus would be the bottom. And you could just do everything in terms of x's. You could do it that way. Or if you look, the parabola is always to the right of the line. So another option we have is, instead of doing top minus bottom, we can do the right curve minus the left curve. And now when we do our limits of integration, we're not integrating from left to right. Well, now we're integrating from bottom to top. So everything is in terms of y now in this. And this is going to happen as we move into this chapter, our next couple of lessons. Sometimes all of our stuff is in terms of x, and sometimes all of our stuff is in terms of y. Well, let's go ahead. So let's figure out where they cross. So I'm going to set 2 minus y squared equal to y. Set up our quadratic. Factor. Solve. So that means these graphs are crossing at y values of -2 and 1. But again, instead of doing top minus bottom, we're going to do from bottom to top, and our functions, we are going to do our right function minus our left function. So 2 minus y squared minus y. But now we're going to put dy on the end. Everything is in terms of y values. And this should look familiar. This is essentially the same exact problem as what example 1 was right here. It was the same equations, except everything was rotated. Well, I guess that parabola is rotated 90 degrees, something like that. But anyway, it's the same area. We're going to get 9/4, no, was it 9/2 for our area. In class, if you think about it, remind me and I can show you how you could do this if you wanted to do top minus bottom, but that's up to you. All right. Good luck on your assignment. Let me know if you guys have any questions.